I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking today with Michael Laine, the president of the Liftport Group. Well, let's start out by talking a bit about your vision. The idea of space elevators has been around for several decades, but you're in the process of turning it into a reality by assembling a company to build the world's first real-life space elevator. Can you give me a layman's overview of what a space elevator actually is?
Sure. Imagine a ball and a string, and you're spinning it over your head. The important part is the string in the middle stays straight, right? So imagine an Earth-sized system where the Earth itself is providing the rotation. You have an ultra-long, ultra-strong ribbon in the middle, and that's attached to a counterweight, an artificial satellite, deep out in space. The basic physics are still the same. The ribbon in the middle stays straight. And once you have that, it allows you to climb back and forth into space. So instead of using rockets that cost $10 to $20 to $40,000 per pound, we feel we can do it for around $400 or so per pound. So it's a huge radical shift from the way we're currently getting into space. It would allow cheap, routine, safe access back and forth, and that's really our goal.
Yeah, this really takes us into the realm of large-scale human endeavor. You know,
Yeah, it's we look at big projects like the pyramids, like the Panama Canal, like the Three Gorges Dam. I mean, all of these things are enormous undertakings, and this, at some levels, it dwarfs them all.
well, what first attracted you to the idea of building a space elevator?
I've always been interested in science fiction. That certainly made it easier, and I was a little more susceptible to the idea, more willing to listen. NASA had done a couple studies over the last couple years, most specifically a study that came out in 2002. And that really was the thing that drove me this direction. The NASA study is by no means conclusive, but it basically draws a roadmap. It draws a picture of the basic technologies. Now it's up to us and a lot of our research partners to take that initial vision and expand on it and refine it. We often say we don't even have all the questions yet, let alone all the answers. But what we do have now, we're pretty excited about.
Oh, sure. Well, a part of transforming that vision is taking it really from the white paper realm and turning it into a real commercial and practical
Right.
vision. And now I was hoping to ask how the project is coming along in that regard.
Well, let's talk about that for a second before we get into where we're at. One thing that needs to be done is you need to broaden your scope of this project. Most people, when they think of that, really focus on the science and technology, and that's fun. I mean, that's important, cool, neat stuff. I mean, that's the kind of stuff that gets you really excited. Um, but every major infrastructure project, whether it's building a bridge or a tunnel or a railroad or a new freeway, they all have four fundamental issues. And if you neglect any one of those four, you will not complete your project. So the four are science and technology, finance and commercial development, social and political issues, and the legal international framework. And so what we do is, yes, we're going after the commercial development, but we also tackle all four of those, and we call them the four pillars, the things that support the project. If you ignore any one of them, you're just simply not going to achieve your goals.
Oh,
And so,
absolutely.
and so it's from those four pillars that has really shaped our business plan. It's really helped us to define who we are, where we're going, what we're doing, what our timelines are, and some of these challenges are really big. I mean, everybody focuses on the ribbon itself, and a lot of people ignore the lifter. The lifter is a really major undertaking. Imagine trying to build a car that you could drive around the planet with without stopping, without refueling, without changing the tires, and without adding new oil. And that's a very major undertaking. Never been done before.
You know, I should clarify really quickly for the audience. When you use the word lifter, that's a description of the device that climbs the tether to
Correct.
the
Yep.
orbital station. And so
Right.
you're not talking about the same thing that we've been experimenting with at American Anti-Gravity, which are very small, lightweight devices.
Right, that's true. We do have a similar. I mean, we use the same word to mean different things. Our lifter is, to really stretch an analogy, it's the railroad car that climbs our ribbon into space. So our railroad car, our lifter, is about. We're looking right now at somewhere around 120 to 140 feet long, relatively thin, and then right in the middle, two great big plates that act as energy systems, where we're beaming power to the lifter. We beam power up to a solar panel that's pointing down towards the Earth. The solar panel converts that energy into electricity. The electricity drives our tank tread motors.
Sure. Well,
So you're right. There's a big difference. Yeah.
you know, in essence, you have a cable. Then it looks like a nanotube cable, at least from the
Right.
direction you're going, and this is 62,000 miles long, right?
Right. Yep.
And at the end of it, it's connected to an orbital platform. Could you tell me a little bit more about the platform itself? Is it going
Sure.
to be a space station or?
Well, we call it a ribbon, not a cable, because it's wide and thin, not thick and round. It helps define this a little bit better. But the space stations that are going to be up there are going to be really whatever the market demands. When they built the railroads from the East Coast to the West Coast, they didn't say you have to farm in Kansas and you have to have beef in Chicago. They let the markets decide what you took from one point to another point. So we're not going to dictate what those operational space stations are. What we think they're going to be are great big solar energy satellite systems, miles on the side collectors of solar power, collecting, essentially free, endlessly renewable, clean energy and bringing that back down to Earth. I mean, that's going to be one major industry that we help propel. And there's also going to be things like recreation, travel tourism. There's going to be medical facilities. One of the reasons people scar so bad when they're burned is gravity affects their healing process. So the assumption is that if you can start to heal in a low G, zero G environment, that'll help you scar less. Other things you're looking at are medical advances in chemistry, so you can make better, more pure drugs for the pharmaceutical industry, better crystalline structures for the electronics industry. Those kinds of things are the things that will develop fairly quickly on these large space stations. And then remember, going back to that ball and the string idea, spin that over your head and you let go, you've got all this excess energy that's going to throw you towards the moon and throw you towards Mars. And so we'll help expand those places as well.
Sure.
And then
sure.
way out in space, 62,000 miles from top to bottom, there's going to be a small artificial counterweight that holds the whole system in place. Imagine, again, the ball and the string. The longer the string is, the smaller the ball has to be for a given rotational rate. And so we could use a much larger satellite, and that would make the string shorter. But we did some cost analysis about what we could reasonably send into space based on prices of a Atlas or Delta rocket, and that's how we really hit the sweet spot of 62,000 miles. So there's a small artificial counterweight deep out in space that holds the whole thing taut.
So the orbital station itself, then, this big ball at the end of the ribbon, is really going to be a zero gravity environment.
Well, there will be a zero or a low G environment around 22,300 miles up. That's where you're mostly going to live, work, and play in space. At the very extreme end, that's not going to be a useful environment. I mean, most people are not going to want to be there.
Oh, okay. Is it because it's
Does that make sense?
rotating? That it would probably be a high negative gravity environment, right?
Exactly right. Exactly right. It would be really high. I don't remember the numbers off the top of my head, but it's pretty extreme.
Oh, sure,
And,
sure.
and what will happen is you'll actually wind up seeing the creation of low G environments, partial G environments, and even high gravity environments, 1.5 and 2 gravity environments for specialized operations. So I think you're going to see an interesting development on the course of this ribbon. As we make it longer and stronger and wider, it'll be able to carry greater payload capacities. And when that happens, you might establish a 1/3 gravity location for people in training to go to Mars. You might establish a 1/6 gravity location for people in training to go to the Moon. So you would have permanent stations next to Earth, right on top of Earth practically, that would allow for the kinds of specialized training that you could really only get in the proper G environment. So I mean, I think this is going to be an evolution. But remember, we're a point A to point B transportation company. We can get you to some really interesting places. What you do after that is up to you. So it's up to the commercial markets to decide how this thing ultimately is used.
Oh, sure. Well,
we're looking forward to it. We're looking forward to providing those services.
The counterweight really is an innovative idea, and I can definitely understand that. It's almost like being on, like being on the merry-go-round, I guess, or maybe as a better example, that carnival ride that spins at high speed. People get up to over 1G environments there just from the.
Oh yeah, and that's exactly what you're looking at.
Yeah. Well, Peter Diamandis from the X-Prize group had suggested that the fuel costs to literally winch a payload into orbit are he had estimated at least around $100. So the $400 price that you're talking about isn't too bad. In fact, that's probably less than the gas cost would be for a 62,000-mile car ride.
Yeah, we're pretty excited about it. Peter Diamandis, a proven visionary in the space community, founder of the X Prize, which he's most famous for, but also the International Space University's partner and founder of Zero Gravity Corp, a partner and founder in Space Adventures. I mean, he really is out there. 20-some years ago, he helped develop a group called SEDS, Students for the Exploration and Development of Space, out at MIT. I mean, he's really been in this community for a long time and certainly has had a major impact. The $100 per pound price, I think, is a little optimistic for the elevator or any other transportation system. I'm a finance guy, not an engineer by trade, and I don't think the $100 mark really takes into account, the cost of money and operational expenses. But really, to go from $10,000 to $40,000 per pound down to $400 per pound, I mean, that's a pretty significant shift, no matter how you look at it. So we're pretty excited about where this is moving.
Oh yeah, well, it sounds like that's around 1,000 times.
Oh yeah.
Yeah. So just imagine NASA having the ability to do a space program 1,000 times as large as they're able to do now for about the same price.
Well, a single space shuttle, one space shuttle, costs between $700 million and $1 billion every time they launch. It's an enormous undertaking, and I believe it's time to change. Now, that's not to disparage NASA. We wouldn't even be having this conversation if they hadn't pioneered the way. My belief is that NASA needs to push beyond the geosynchronous environment, beyond 22,300 miles, and really needs to put their efforts into the development of the Moon and Mars and go out to the further planets and moons. That's an area that commercial development just can't go. They can't take on that kind of enormous price tag, whereas Uncle Sam can do that, and they can improve a lot of the technologies along the way. Now that we're starting to develop the commercial technologies to handle low Earth orbit and geosynchronous orbit and suborbital flights, I think really NASA needs to push a little bit further out. But thanks to the commercial efforts that the X Prize and Lockheed and Boeing and all those guys have really made something amazing transform, and we want to be a part of that.
Oh, absolutely, absolutely. Well, it sounds like now that the entire 62,000 miles isn't what people would travel. They would be traveling around 22,500.
Right. Yeah.
Now, in terms of,
about 22,300 to Geo, but it's pretty close to that.
I guess I'm thinking in terms of driving. I know to drive across the United States 3,000 miles, it takes round about a week. And a lot of that is sleep time or rest stops and stuff like that. So I'm kind of wondering, aircraft, I guess, can get it down to around 6 hours, but
Right.
22,000 miles is considerably longer. It's what, 7.5 times the
Sure. Yep.
distance.
So what we're going to wind up doing is the lifter, our railroad car, if you will be traveling about 125 miles an hour, and it could probably go faster than that, but technically it starts adding some complications we're just not tackling right now. So that takes about a week, because it never really stops. So it takes about a week to get to Geo. One thing that we have to be concerned with is radiation. So it looks like in the early days, until we can get a very, very large capacity elevator, what may happen is you travel up a certain distance up to basically out of the gravity well to low Earth orbit or a little higher, and then drop off in a rocket to get you the rest of your destination. Once we've made this ribbon wider and stronger, that allows for faster travel and higher radiation shielding. So those are factors we're going to have to really consider when we're doing this.
Sure.
There's no point in doing this. I mean, there's no fun point in doing this if you can't go. Like, if you and me can't get on this thing and take a trip, I probably wouldn't be doing it at all. So we're looking at, the constant safety and concern for our customers, our passengers. So,
Well, speaking of radiation, I saw a photo from one of the astronauts' spacesuit helmets, and this was on one of the moon missions, and they showed a kind of a microscopic view of it, and the cosmic rays, just small high velocity projectiles, basically punched little holes through it, like it almost looked like miniature shotgun blasts. And I'm wondering, with nanotube materials, are you going to have problems shielding that from stuff like cosmic rays that could damage the structural integrity of it?
Well, there was an experiment called LDEF, what did that stand for? I forget what the initials stand for, but the experiment was essentially put a variety of materials out in space for a long duration and evaluate what happened. Now, this LDEF test took place before carbon nanotubes were readily available, so we don't have any specific data on it right now, although there is something that's that's in the works. Carbon nanotubes are a very pure carbon molecule, which is one of the things that makes them so incredibly strong. They're not likely to be affected by any sort of radiation. Now, on the other side, though, is right now, it looks like we're going to have to put the nanotubes into some sort of composite, some sort of matrix. So we're going to have to mix the nanotubes in with some very sophisticated binding material. So the nanotubes were not very concerned about radiation or atomic oxygen, but we're very concerned about the binder material, whatever that might be. And so those are concerns we're going to have to address. And so Simple solutions are for atomic oxygen regions or something like that. Coat the outside of it with some sort of metallic that would basically seal the nanotubes.
Oh, sure.
And their composites. But like I said, we don't even have all the questions yet, let alone all the answers. Right now, we're working off of good theory to tackle some of these problems, and really, honestly, what we need is a lot more research.
Well, the ribbon cable that you've described, I can almost visualize that as kind of a freeway to the stars, I guess.
Yep.
And one of the things I was wondering about was what made you choose a ribbon shape as opposed to the more traditional, round cable?
Sure. That actually is a pretty old idea. If you look at some of the more scientific studies, the science fiction really propagated the idea of a cable. But if you have a small, minor nick on the edge of a cable, you've seriously degraded the carrying capacity of that cable. And we know we're going to get hit on a pretty frequent basis because there's a lot of debris up there. So we're going to take a lot of little nicks on the edges. And after a pretty short time, the structural integrity of this cable is really going to be suspect. And there's not a good way of repairing it. So instead, the idea was we would make it this wide ribbon, and in our case, the early days, it's going to be 3 feet wide and about paper thin. And by making it wide, the exact same debris that hits you, that hits your cable and significantly impairs it, that same thing traveling the same location, the same direction, the same speed, will have just a very minor impact. It'll pass right through the ribbon and almost not even be a significant factor. You'd have a pinprick hole as opposed to a major damage. Does that make sense?
Oh, sure,
Okay.
absolutely.
So the other part of it is, the first part is make it wide. The next part is make it slightly curved. And by making it curved, it eliminates the possibility of this one magic bullet that comes in at exactly the right angle to cut the thing right in half. By making it curved, there's no single trajectory that could possibly cut it completely in half. So it's those kinds of details that we're starting to work out. And you got to understand that this is definitely a work in progress. We feel that it is a 15-year project, of which we're on year number 2. So we'll refine this design as we go. For example, the baseline out of the NASA reports, we've really expanded on quite a bit. We've revised the ship, the Liftport that's out in the ocean. We've revised that. We're on our 4th significant revision there. We're on our 3rd significant revision at the counterweight. And really, our claim to fame is the robotics. We've now made 16 robots. We're working on number 17 that's specifically designed to climb string. And every time we do that, we make fairly significant discoveries. So our first robots are very, very different from our current robots.
Yeah. Now, in terms of test prototypes,
Mm-hmm.
you're planning a 1-mile balloon tether test, if I remember right.
Yep.
And so that would really capitalize on your ability to build and upgrade these robots periodically.
Yeah, we're really looking forward to that. We have a bot that, within laboratory conditions, will easily climb a mile. We've done that a number of times. However, what you can do in the lab is not always what you can do in Mother Nature's territory. So we really do need to get out into the wild blue yonder and put a high-altitude balloon up, tether it to the ground, and have our lifter climb back and forth. We need to do that a lot. And so we're in the process right now of doing that. Pending FAA approval, we should be able to do it by the end of summer. We've got a series of tests. One is actually next weekend. We're going to go 150 feet, then 300, then 500, then 1,000, and just keep incrementally moving forward. because a machine that works perfectly at sea level is actually a very different machine than one at uh, at 5 or 6,000 feet. You start getting colder and colder and colder. Now, we're not going to have a problem with that, we don't think, because we went out and we did this off the side of an MIT building, the green building. It's the tallest building on MIT's campus. And we had a ribbon cantilevered over this side of the largest building there, and we climbed back and forth in the beginning of a snowstorm. It was around 30 degrees. The wind was blowing 20 to 25 miles an hour, and it was an 8-hour, 4-inch dump of snow that we started in. So, pretty exciting conditions. We feel pretty confident that we can make that first mile pretty easily. The next mile, the temperatures drop, dramatically, and that next mile actually is going to be pretty challenging. So, as we get further and further, our internal joke is one down, 61,999 to go, in terms of the length of the ribbon that we're going to have to climb. So, we're getting there. But it depends on the FAA to approve our test. And they've been really cooperative. They were pretty surprised when we showed up and knocked on their door, but since then they've really tackled this with a lot of conviction. So it's been really helpful.
Well, on the business side of things, you have a couple of customers already involved with this, don't you?
We do have some. I'm stealing a line from another guy in the space community, John Powell. He said, "We don't need investors, we've got customers." Well, we don't have that many customers, so we're actually happy to have investors and customers. But so we've got some people that are they're intending to buy our nanotubes. We've got a factory that we're putting into place right now out in New Jersey, where we'll actually be making carbon nanotubes by the end of this month for sale. I mean, that's a major transition. So we've got the hardware of our robots and the hardware of our nanotube furnaces, and we've got people that are interested in buying, both products from us. On the robotics side, we'll provide high altitude observation platforms. So we'd have cameras and surveillance equipment and cellular communications equipment and things like that at the top of the ribbon, and then the lifter provides some of our tools. So we got customers there, and we've also got customers interested in the nanotubes, looking to develop whatever we can of a super strong, super lightweight material.
Oh, sure.
So, yeah, we're pretty happy about where we're at. We're at that very bumpy stage between being a PowerPoint concept, where all we had was pretty pictures, into actually having hardware, actually having production facilities for our nanotubes. Right now, we've got 4 walls, a ceiling, and a roof, and a big empty room out in New Jersey, and our furnaces are under construction. We'll have our first one out there. We take possession of our lease July 1st. We'll have our nanotubes in production by the 15th. So pretty excited about that. And our goal is to have 11 furnaces by Christmas. So
that's
yeah,
wonderful.
we're really excited about how this is evolving. It's moving very quickly.
Yeah, it is amazing to see it come along. The space elevator seems like such a daunting task in so many ways that to see this kind of progress is just remarkable.
Well, it is a daunting task, but without being really cheesy, what's that? The journey of 1,000 miles is the first step. Begins with the first step. I mean, if you break all the pieces down into bite-sized, manageable pieces, it suddenly makes more sense. And so there's this very clearly defined timeline of, if we want to have this thing in place by April 12th, 2018, what has to happen before that, and what has to happen before that, and before that, and before that. And we work our way all the way backwards till this afternoon. And no, our plan perfectly detailed, but we have really very clear milestones of what has to happen at each stage.
Oh, sure. Well, investors, the public, and potential customers can reach you online at www.liftport.com. And in addition to photos, video, and detailed information about your projects, it also features a countdown timer to April 2018.
Right.
I'm wondering how you arrived at that scheduled date, and are you on track for a working space elevator within this 13-year period?
We're definitely on track. I actually suspect we're slightly ahead of schedule for two reasons. One, the nanotube production is going along much faster than we expected. And two, honestly, the credibility of this project has moved faster than we anticipated. We are today where I thought we would be in another 3 years in terms of acceptance from the public and private sector. So that's really helped us move forward faster than we expected. But April 12th, well, let me give you the year first. 2018 came about because the literature said we could, it was possible within 15 years. The NASA study said it was possible within 15 years. And so we took that date on as a very specific challenge. Now, when people talk about doing these large tasks, they always generalize. Oh, it'll take 5 years. It'll take 25 years. Fusion's only 20 years away. And they always come up with really generalized numbers, and nobody's really being committed to accomplishing it within a specific date. We didn't feel that that was the correct approach. When a city or a state takes on the task of constructing a new bridge, there is an expectation of that contractor to have that bridge completed by a particular time. Otherwise, there were penalty clauses in the contract. We felt that it was much smarter to take that approach, to be really dedicated to a specific date. So the literature said it would take 15 years. We started in 2003. That put us, that kind of assigned the deadline of 2018. Now, we've been working on it for 2 years now, and somewhere along the line, we actually had the official launch date of the 4th of July, Independence Day. It seemed to make sense for us. We had looked at July 20th as the first day we walked on the moon. Both of those were pretty good for us, and we were pretty happy with it. And then, as we started to embrace the international community, and the international community started to care about what we're doing, we started getting this feedback that was basically saying, look, the 4th of July is an important date to one and only one country. So if this is going to be a global project, you need to modify that. And we looked and we listened, we thought about it for a second, and it was obvious, okay? So we did need to make a change. We modified our date as a result of that. And the date that we picked, April 12th, we are very happy with now. It was the anniversary of Yuri Gagarin traveling around the planet for the first time, and it's also the same anniversary of the Columbia taking off for the first time. So it's both a significant date for the two spacefaring powers, the Russians and the Americans, at the time. Obviously there's, a third spacefaring power out there in China, but we had established our date before they were involved.
Oh, sure. Sure.
So that's how we picked the date, April 12th, 2018, and that's why we have a countdown clock on it.
Well, and I'm definitely going to stay tuned to your results. And again, people can learn more about it at www.liftport.com. Well, we're almost out of time for today, but I was wondering if you might have any parting words for our audience. And again, thank you for your time.
No, nothing we haven't already covered. Just stay tuned. We have a very active community. If people want to get involved with our message boards or sign up for our newsletter, I'd strongly encourage that. They can send email to info@liftport.com. The newsletters really help tell the story on a really timely basis. We publish, if you're an investor, you get 4 a month. If you're the general audience, you get 3 a month. And We're just about to launch something that is a little different. We're actually developing a comic book type newsletter. And we're also developing what we call the Art of the Space Elevator newsletter. And then there's, of course, the general interest one. So it should be pretty entertaining. We definitely want to keep people involved with what we're doing, and that's probably the best way to get current information to sign up for the newsletter.